Hey, I'm going to be talking about our paper on using electrical flows for oblivious routing with low competitive ratio. What we're going to be doing is routing on graphs. These are undirected graphs which have n vertices and m edges. And this particular graph I'm going to keep using in my examples. So I'll just give a naming scheme for the vertices. I call the columns as A to D and the rows as 1 to 5. So for example, this would be the B2 vertex and the bottom one would be the C4 vertex. And what we get is a sequence of routing requests. For example, this could be a sequence where from A3 to D3, so the leftmost to the rightmost vertex, you need to send 5 packets. And then there's 1 packet each in the middle vertices from BI to CI, except for the last one. So you need to send 4 packets between the middle vertices each, and 5 from the leftmost to the rightmost one. And what's your goal when sending these packets? You want to minimize the maximum number of packets that go across a single edge. And this is what is called as congestion of the routing. So you want to make sure that no single edge gets too many packets across it. The goal is to find such a routing. Now, suppose you are allowed to look at all the requests before you route. Then what would the optimal routing be? So this is what you call as the offline setting, where the requests don't come in one by one, but you can see all of them and then route it. So for this particular set of requests, what you would do is send the single packet each directly across the single edge connecting them. Now you have 5 packets you need to send from A3 to D3. You could send one down here, a couple across like this, and another couple across like this. Now every edge has at most 1 packet going through it. And so the congestion of this particular routing is 1, which is the lowest you could get, right? What's the problem with this? This assumes that you know all the routing requests in advance, which is not usually the case. Usually you get the routing requests in an online fashion, where first you route a request, and then you get a request which you need to route after this, right? So one way you could do this is using traffic aware routing, where you've routed some requests already, and now when you get a new request, you look at where you've routed the previous requests, you look at the congestion of all the edges which exist, and try to route this new request along some low congestion path. Try to see where previous requests haven't been sent and send it along such a path, right? But that's not the kind of routing we'll look at now. We'll look at something different called oblivious routing, where you don't look at how other requests have been routed. If you get a single request, you route it by itself using some algorithm which is independent of how you have routed the previous requests and the future requests. Right? The nice thing about this is you don't need to remember how previous requests were routed, so it's much simpler to implement. All you need to do is look at your current request and route it in some way. Of course, it's going to have worse congestion because you're not taking all the information you have into account. And the question is, how much worse could this be? This is what we need to bound. The ratio of what is the congestion for our oblivious routing by the congestion induced by some optimal routing, and by here and here by optimal, we mean it can see all the requests in advance. Right? And this is what we call as competitive ratio of the routing, This is common in online algorithms. So how would you get an oblivious routing? Well, for starters, you could try this. Suppose I say an oblivious routing is as follows. I give one path between every pair of vertices, and suppose I am asked to route 5 packets between S and T. I just route these 5 packets along the single path which I've provided. This could be an oblivious routing. And for a concrete example, think of a spanning tree of a graph. So this is the same graph we had before. This is a spanning tree of the graph. Now, suppose I get a request between B2 and C4. Then if I want to route it along the spanning tree, this is how I would route that request, right? The nice thing is there's a unique path between every pair of vertices along the spanning tree. So it's very easy to know how I'm going to route the packets every time. The problem with this is if you look at this middle edge of the spanning tree, lots of packets are going to need to use this edge. Why? Because anytime I route from the left side of the graph to the right side of the graph, the only edge of the spanning tree which connects these two sides is this middle edge. There are lots of other edges which go across, which could have been used, but you only have this edge. And so it's going to get a lot of packets going through it. And if you want to think of a concrete set of requests for which this spanning tree is going to be bad, suppose I think of this simple set of requests. I take every edge in my graph and I ask to route one packet across this edge. This is simple, right? Now, if I do this optimally, what can I do? Well, I know that for every edge, I'm going to request one packet across it. So I could just send that request across the same edge. And so optimal congestion is going to be 1 because every edge has one packet going across it. But what's going to happen on this tree? Well, you see that most of the edges in the graph are across from B to C. And for each one of these edges, it's going to need to route it across the middle spanning tree edge. And so the congestion of the middle spanning tree edge is going to be as large as the number of edges which go from B to C, which is at least M, right? So the congestion in this spanning tree is going to be as high as M, whereas the optimal congestion is 1. So this has competitive ratio M, which is not very good. Ideally, what you want is to get something polylogarithmic in M and N. Okay. The question is, okay, this is bad. Could you do something else? Is there a better routing? There's a theorem by Borodin and Hopcroft, which says if you give a single path between every pair of vertices, it's going to be bad. Formally, it shows that the competitive ratio is going to be square root of n. So you do the only thing you do when you have these kind of problems. Instead of having a deterministic path, you sample from a probability distribution over path. And anytime you get a demand, you sample one of these paths and route it along that sampled path. So the congestion is the expected congestion. And it turns out in this case, you can achieve competitive ratio of log n. This was a theorem by Harald. So how do you get an oblivious routing which has good competitive ratio? Let's look at an example of one algorithm. So the problem with a single spanning tree was that every edge which does not belong to the spanning tree has very low congestion, 0 in fact, because there are no packets which are routed across it. And there are edges which belong to the spanning tree which have linear in M congestion. So there are really bad edges and there are really good edges. So the idea is to get a set of spanning trees where the set of backed edges are sort of different each time. And so on average, each edge doesn't have really bad congestion. And so if you choose one of these uniformly at random, then this in expectation is going to have low congestion. That's what we want to do. We need one piece of terminology for this, which is the load on an edge induced by a routing. So this essentially says for every routing, there is some sort of worst case demands which you can ask for it. This load on an edge is just a number which says what is the congestion on edge E when I route this worst case demand using the routing R. So this is essentially saying how bad is the routing R for an edge E. To have an example, if we go back to the spanning tree routing, then all of the orange edges have load 0 because there is nothing being routed across this edge by the spanning tree. And the middle edge has congestion, has load linear in M, right? And just to rephrase what we had before, earlier what we wanted was, we wanted the congestion to be low. In this new terminology, what that means is we want to find a routing where the maximum load on any edge is small according to this routing. So regardless of the worst case demands, the load on every edge has to be small, ideally polylog n, which is what we want, right? Okay, with this piece of terminology, let's go on. What we're going to do is just multiplicative weights update. For every edge, we give it uniform weights initially, and iteratively we do the following. We find a spanning tree which has low average load according to these weights. So recall that our final goal was to say the maximum load was low. Now we're saying, oh, we don't need the load on every edge to be low, but rather if we take the average of the loads on all the edges with respect to some weighting W, then this is low. Now once we find this, in the next round we want to find a different spanning tree. So what do? Essentially we want the next spanning tree to be good on edges where the current spanning tree is bad in some sense, right? So if an edge has a high load now, we're going to increase the WE so that in the next iteration, in the average, it plays a higher role. And so the load on that edge will be low in the next iteration. And if it has low load now, then we decrease WE. We reduce its importance. And the two things which determine, the two parameters of this algorithm are the number of rounds and what is the average load. The number of rounds is going to depend on how bad a load is for a single spanning tree. In the example we saw, this was about M. So the number of rounds is going to be proportional to M. And we want an average load spanning tree. And it turns out you can do this using average stretch spanning trees. And you can set, this duality was shown by Räcke and Anderson-Feige. But if you want a low average stretch spanning tree, then you can use Abraham-Neyman spanning trees, which gives you sort of log n, log n guarantees. So this is not the best, but it gets you pretty close. Right? So if we have these two ingredients, then we get a O tilde of log n congestion oblivious routing. What we do is we reduce the iteration count of this at the cost of a slightly worse approximation ratio right now. The idea is to go from L1 minimization, which is spanning trees, to L2 minimization, which is electrical flows. What are electrical flows? Well, you take your graph, look at each edge as a resistor, and if you want to route from S to T, then you set a voltage between them such that there is 1 unit of current flowing between S and T. And for example, in this example, this would be the way of doing it. And now if you have a flow from S to T, then you can decompose it into paths. And so this gives you a probability distribution over set of ST paths, which is what you want for an oblivious routing. You essentially want a flow which gives you probability distribution over paths, right? Okay, then how do you route it? You route it along one path you sample from this electrical flow. The first thing I want to say is that this is a strict generalization of what we had before. Why? I want to say any spanning tree routing, you can think of it as an electrical flow routing. Why? Suppose I set the resistance of every edge which doesn't belong to the spanning tree to infinity, and the resistance of every edge which belongs to the spanning tree as 1, then it's not very hard to see that routing electrical flow along this resistance network is the same as routing along the spanning tree. So now essentially what we are allowing is, we're allowing the resistances to be something other than 1 and infinity. This gives you general electrical flows, right? And so earlier we found a spanning tree. Now we want to find resistances such that electrical routing according to these resistances has low load. Okay, so what were the two parameters before? It was the K and what was the low average load. These were the two parameters we had for spanning trees. And it's going to be the same now. So we want to find resistances such that K is low. And for K, what was the goal? The goal was to find a bound on what was the worst load on any edge. In the case of spanning trees, that was M. For electrical flows, for the resistances we give, it's going to be root M. So you get a square root of M improvement. And the average load, if you use spanning trees, low stretch spanning trees, it was log n, log n. And we are going to use a result of Shield, Rao and Srivastava, which gives you log squared n instead, still polylog. And what is this resistances that we set? So we claim that if you set resistances exactly equal to WE plus 1 over M. So WE, recall, what you wanted was low WE average load. So on edges where WE is high, you want to send lesser current through it. And so you want to set a higher resistance. So this makes sense that if WE is higher, you want to set your resistance to be higher. And this part of the resistance, in some sense, bounds the average load. And the 1 by M part makes sure that every edge is sort of close to uniform. And this bounds the maximum load by root M. Let me expand on this a little bit. So first, so these are the resistances we have, WE plus 1 by M. First, I claim that if I just set my resistance to 1 by M, then the maximum load is at most root M. Why? Because if we set uniform weights on a spanning tree and do L1 minimization, we got a bound of M. Now we're doing L2, so you would expect root M, which is what you get indeed. And for the second part, if you set the resistances to be exactly the weights for which you want low average load, then there's a theorem by Shield, Rao and Srivastava, which says that, so what we used for spanning trees was low average stretch spanning trees. And this theorem morally tells you that the stretch of electrical flows is low. It tells you that electrical flows are not much longer than shortest paths. They're at most of log squared and longer than shortest paths on average. So we use this to get the second bound. We can put this together to get the result that we want. Square root of M iterations and a log squared n guarantee on the competitive ratio of the oblivious routing. Thank you.